Hello friends, our today's title is Pleochroism, Interference Colors, Extinction Angle and Twinning. Introduction. Minerals are characterized by certain definite physical properties, chemical composition, optical properties and internal molecular structure, and hence the study of minerals is made under different heads like physical mineralogy, chemical mineralogy, optical mineralogy and X-ray mineralogy. The properties such as pleochroism, extinction and extinction angle, twinning and accessories of transmitted light microscope are all dealt under the head optical mineralogy. Optical mineralogy deals with the study of optical properties of minerals in thin sections and grains under a special type of microscope. Pleochroism. Minerals are white or colorless when pure. When color is present in minerals, it may be due to minor impurities, in some cases found as inclusions. But mostly the color of a mineral is due to its own property of absorbing light of certain wavelengths from white light, the remaining wavelengths being transmitted. In isotropic minerals, since light travels with equal velocity in all directions, its vibrations are equal in all directions and the absorption for any color of light is the same in every direction. Therefore, there is no change in color when the microscope stage is rotated. In anisotropic minerals, ordinary and extraordinary rays travel not only with different velocities, but also with different absorption effects. In anisotropic minerals in which light is resolved into two sets of vibrations, fast that is X and slow that is Z, that is uniaxial minerals, the ordinary and extraordinary rays have unequal absorption power, resulting in change of color along the fast and slow vibration directions under plain polarized light that is without analyzer. In biaxial minerals, however, light is resolved into three sets of vibration X, Y and Z, and the unequal absorption power of the ordinary and extraordinary rays results in the color change along these three vibration directions. This property of a colored mineral in which the color change is observed under plain polarized light is called in general pleochroism. Pleo means many and chroism means color change. In uniaxial minerals, the color change along the vibration directions is twofold since there are two vibration directions X and Z and is also called dichroism. But in biaxial minerals, the color change is threefold since there are three vibration directions X, Y and Z, and it is referred to as pleochroism. Isotropic minerals are not pleochroic or dichroic since there is no color change at all. Pleochroism is normally expressed as a formula or scheme by relating the color changes to the different vibration directions as follows: tourmaline, X, colorless, pale yellow; Z, pink, green, blue. Z is greater than X. Hornblende, X, pale yellow, Y, green, Z, bluish green. Z is greater than Y and Y is greater than X. For determining pleochroism of a mineral, it is necessary first of all to determine the different vibration directions in the mineral. By the usual method, each of these vibration directions is next brought parallel to the vibration plane of the polarizer, that is horizontal cross wire or vertical cross wire. Since this property is observed in plain polarized light only, the colors noticed in these positions are recorded and finally related to the particular vibration directions. Thus, the pleochroic formula or scheme is derived. After the derivation of the pleochroic formula, the degree of absorption along the different vibration directions is estimated by observing the intensity of the pleochroic colors present along these directions. For example, in the case of hornblende, which shows the pleochroic scheme, X equal to pale yellow, Y equal to pale green, Z equal to bluish green. The color of lowest intensity, that is least absorption, namely pale green, appears along X, and the color of greatest intensity, that is greatest absorption, namely bluish green, appears along Z, while pale green color of intermediate intensity appears along Y. And in this case, the degree of absorption is expressed as Z is greater than Y and Y is greater than X. This expression indicating the degree of absorption is called the absorption formula. Hence, the pleochroic scheme in minerals is recorded by expressing the pleochroic formula accompanied by the absorption formula. When polarized light enters an anisotropic substance, it splits into two rays vibrating at right angles to each other, one vibrating slowly in the direction of higher refractive index and the other vibrating more rapidly along the direction of lower refractive index. In other words, when the two rays leave an anisotropic substance, the ray vibrating in one direction is retarded with reference to the ray vibrating at right angles to it. This kind of movement results in a path difference for the two bundles of polarized light, and they are made to pass through upper polarized or analyzer, whose vibration is placed at right angles to the first polarized. When these two sets of rays vibrating at right angles to each other have a certain path difference enter analyzer, they are resolved into vibration directions of analyzer and they interfere with each other. In this process, some components are extinguished while certain other components are enhanced. The component or color whose wavelength or integral number of wavelength is lambda 1, lambda 2 to lambda n matches with the amount of retardation. The fast and slow rays are in opposite direction and they interfere destructively and are consequently eliminated from the spectrum. When the amount of retardation is equal to say half lambda or 1.5 lambda or 2.5 lambda of a component, the two rays resolved are in same direction and they interfere constructively and the light passes with maximum intensity. Ultimately, it is this component of light or color that is perceived by the eye. This color is known as interference or polarization color. If the amount of retardation is 0, all wavelengths interfere destructively, yielding darkness, that is, the substance is isotropic. The interference color is controlled by three factors: thickness, birefringence, and orientation of the crystal. Isometric crystals and amorphous substances having the same value of refractive index in all directions obviously do not produce any path difference when the two sets of rays emerge out of the crystals. In this case, as explained earlier, all the components of the light rays oppose each other and get cancelled. Thus, these substances remain dark in all orientations between the crossed polars. In other words, they are isotropic. Extinction and extinction angle. Extinction is an optical property of an anisotropic mineral by which the mineral shows darkness in the field of view under crossed Nichols. Extinction occurs whenever a vibration direction of the mineral coincides with or is parallel to a cross wire under crossed Nichols, and a mineral shows 4 such positions of extinction at intervals of 90° during a complete rotation of the microscope stage. In between these positions of extinction, the mineral shows illumination with interference colors, but in position at angles of 45° from the extinction positions, the illumination shown by the minerals are again at intervals of 90°, alternating with the extinction positions during the complete rotation of the stage. The type of extinction shown by the minerals is determined as follows. The given mineral section is fixed on the stage of the microscope with this prominent edge or cleavage lines parallel to any of the cross wire horizontal or vertical, and the stage reading is recorded. Let us suppose the reading is 0°. Then the mineral section is observed under cross Nichols. If the mineral section shows darkness, extinction, the vibration of the mineral coinciding with the cross wire, that is the extinction direction of the mineral, is parallel to and coincides with the crystallographic direction indicated by the edge of the cleavage lines of the mineral. This type of extinction is identified as the straight or parallel extinction. Then the stage is rotated through an angle of 90°. When the stage reading is recorded at 90°, and in that position it is noticed that the edge or the cleavage lines is parallel to the vertical cross wire, when the mineral section shown again darkens. Similarly, the extinction position should be checked up at the other two positions during the rotation of the stage at 180° and 270°. If the mineral section shows illumination with the interference colors in the position, when the edge or cleavage line is parallel to either horizontal or vertical cross wire and shows darkness or extinction, is in a certain position during the rotation of the stage, when the edge or cleavage lines of the mineral is inclined to the cross wires, the type of extinction is identified as inclined or oblique extinction. In this case, the extinction direction, the vibration direction of the mineral coinciding with the cross wire, does not coincide with or is parallel to the edge of cleavage lines, crystallographic direction. Therefore, the type of extinction is identified as the inclined or oblique extinction. In such a case, the angle between the extinction direction, that is the cross wire coinciding with the vibration direction of the mineral, and the edge or cleavage line, that is crystallographic direction, is called the extinction angle. It is determined as follows. The stage reading is recorded at the position of the mineral section in which its edge or the cleavage line is parallel to any of the cross wires, say horizontal cross wire or vertical, when the section shows illumination. Now, let the stage reading be 60°. At this position, the vibration direction of the mineral are inclined to the cross wires and also to edge or cleavage lines of the mineral section. The stage is next rotated anti-clockwise till the mineral section shows total or maximum darkness or extinction, and the stage reading is noted again. Let it now be at 90°. At this position, the vibration directions of the mineral section coincide with the cross wires, extinction directions, that is, which are inclined to the edge or cleavage lines of the mineral section. Then the difference between the two readings of the stage is noted, and it is in this case 30°. This angle of 30° is the angle between the crystallographic direction indicated by the edge or cleavage lines of the mineral section and one of the extinction directions, namely one of the vibration directions coinciding with horizontal cross wire. Since the angle measured is 30 degree, which is less than 45 degree, it is expressed as the extinction angle of the mineral under observation, since the extinction angle of the mineral is the angle between the crystallographic direction and the nearest extinction direction in this case, the vibration direction coinciding with the horizontal cross wire. In the measurement of extinction angles, it is also to be remembered that if the angle obtained by measurement is above 45 degree, its complementary angle 90 degree minus the measured angle is expressed as the extinction angle of the mineral. But if the measured angle is 45 degree or less than 45 degree, this angle itself is expressed as the extinction angle of the mineral. Since the extinction angle of a mineral is the angle between its crystallographic direction and the nearest extinction direction as stated earlier. Twinning. In a homogeneous crystal aggregate, if all the crystals occur in parallel position with a similar crystallographic direction lying mutually parallel, the case is one of parallel growth. If, on the other hand, the parallelism is only partial and the two halves of the crystal thus related show some of the crystallographic directions oriented in oblique disposition, the case is of twinning. In twinned crystals, the two halves occur with some re-entrant angle lying in between them. The basic nature of atoms in crystals is to orient in definite directions. For example, parallel, 200 and 111. Rarely, arrangements of atoms is seen to reverse along certain planes, with the result optical constants and various properties like electric conductivity get reversed. Such configuration results in twinned crystals. A twin is defined by composition plane, twin axis, twin planes and twin center. A compositional plane is a plane along which two twinned individuals are attached together, wherein there is a reflection of the lattice arrangement and crystal constants by a mirror plane. Twin axis is an axis about which various crystal constants are rotated, usually by 180 degree. Twin plane lies normally to twin axis. Inversion about a point is called the twin center. Twins are normally defined by certain twin laws. For example, Dauphin law of quartz. In twinned crystals, depending upon the style of reversal arrangement, twins are classified into normal, parallel and complex twins. In normal twins, the twin axis lies at right angles to the composition plane and twin planes lies parallel to each other. For example, L-bite twin and Mackle or twinned octahedron in diamond and spinel. Twin axis in a parallel twin lies in the composition plane, with composition plane and twin plane disposed at right angles to each other. In a similar way, complex twin can be explained as combination of normal and parallel twin, when two twinned individuals can be separated easily along the composition plane. They are termed as contact twins. If only two twinned individuals exist, they are simple twins. But when many individuals are attached with their composition planes parallel to each other, they are termed as polysynthetic, multiple or lamellar twins. In some cases, the two individuals grow by cutting each other across, resulting in penetration or interpenetration twins. The two twinned individuals in such cases can hardly be separated from each other. In certain cases, composition planes of a polysynthetically twinned crystal do not lie parallel to each other, resulting in cyclic twins. Often, the symmetry of a crystal belonging to a lower symmetry group increases on twinning, and such twins are referred to as mimetic twins. Based on genetic relationship, twins are defined as A. growth twins, B. transformation twins, C. gliding twins. In growth twins, twinning takes place at the time of growth of the crystal. In case of transformation twin, twinning develops subsequently to growth. For example, M twinning or cross-hatched twinning in micro, Klein and Dauphin law in quartz. If the twinning develops during a deformational event, it is called gliding twin or deformation twin. For example, twinning in corundum and cordierite. Gliding twin in corundum results in the development of parting planes. This type of twinning has great significance in distinguishing natural ruby and sapphires. The phenomenon of twinning is very well visualized in thin sections under the microscope. Since within the individual components of the twins, some of the crystallographic directions are not parallel, and naturally both the twinned halves cannot undergo extinction simultaneously. The two twinned halves shown between crossed nickels a sharp and straight line of separation, and while one half is in extinction, the other must exhibit interference color. The mineral plagioclase very commonly shows what is known as lamellar twinning, since due to repeated twinning, narrow lamellae of the mineral occur in juxtaposition. Crystals of the same species growing in a melt have a tendency to get attached together, which may appear like twinned crystals. These are not twins in the true sense, but this process is called syneiosis. Accessories of transmitted light microscope. The main accessories of the transmitted light microscope are quartz wedge, gypsum plate, mica plate and universal. U-stage quartz wedge consists simply of a very thin tapering wedge, the faces of which are approximately parallel to the prism of a quartz crystal. It is mounted on a narrow glass plate marked with the letter Q and an arrow marked X, indicating that of the two directions of the vibration of light in the wedge. The one which is parallel to this direction of the ray propagated with greater velocity, and if marked Z, indicates that this is the direction of vibration of the slower ray. As the thickness of the quartz increases, the sequence of the color in the following order: violet, blue, green, yellow, orange and red is repeated distinctly 3 times, corresponding to the first, second and third orders, with fainter and unclear color beyond. An important application of the quartz wedge is in determination of the order of interference colors of anisotropic minerals under crossed polars. Gypsum plate. This is a thin plate of gypsum mounted between two plates of glass with an arrow marked either X or Z, indicating respectively the direction of vibration of the faster or slower ray. The name sensitive tint is given to this because a slight increase of the double refraction gives a blue color and a corresponding decrease changes the color to yellow. This is used mainly to determine the direction of vibration. X or Z. In the anisotropic minerals under crossed polars, and accordingly the zinc with negative yellow color, subtraction, and positive blue character with sensitive tint color, that is addition. Mica plate. This is a sheet of muscovite mica cleaved so thin that of the two rays of the light passing through it, one has gained 1/4 of a wavelength in phase over the other and is usually mounted between long and narrow glass plates. This is also known as 1/4 wavelength or 1/4 lambda mica plate. It is used in testing an interference figure. For this, it is inserted between the polarizer and analyzer through the slot in the tube above the objective and is so oriented that the Z direction makes an angle of 45° with the planes of vibration of the Nichols. After its introduction, if the isogears of the interference figure of a mineral in the direction of the introduction of the plate move closer, then the mineral is positive, and if they move away, it is negative. Universal stage. The figure helps in orienting the minerals in thin section in all the three directions by allowing the section to tilt in any desired position in space. It has either 4 or 5 axes corresponding to 4 or 5 flat rings, with the ring 5 carrying ring 4, ring 4 carrying ring 3, ring 3 carrying ring 2 and ring 2 carrying ring 1. Ring 1 and 4 rotate on vertical axis through the center or the U state. Ring 3 and 5 rotate on east-west axis and ring 2 rotates on north-south axis, with direction north being away and east-west being parallel to the observer. The U stage helps in determining optical constants of an anisotropic mineral, twin schemes of feldspar and other minerals, and for petrofabric study of rocks. General optical characters under transmitted light microscopy. The properties that help in mineral identification by the transmitted light microscopic study are color, habit, pleochroism, relief, cleavage, isotropism, and anisotropic properties such as twinning, interference figure, and extinction angle. Today, we have studied the optical properties such as pleochroism, interference color, extinction angle, and twinning are important for the identification of individual minerals or minerals present in rock. The optical properties mentioned not only serves to identify the minerals, but also helps in distinguishing the minerals, showing the identical optical properties. Thank you.